Thank you very much for the invitation to this nice conference. Yeah, I was visiting KITP about 7 years ago, and I'm very happy to come here again. Yeah, and my talk is based on work with Mitatunza, which is already 4 years ago, and another more recent work with a great postdoc, Yui Hayashi at Yuka Institute. And looking at the program, I learned that Georg's talks on Wednesday are closely related, and my talk is completely continuum, but I learned that his talk is about lattice, so accidentally my talk fits to the theme of this conference, continuum and lattice. Yeah, and the purpose of my study is to understand the confinement of 4D gauge theories, but it is strongly coupled, so we want to deform the theory by considering putting this theory on R2 times T2 with a specific boundary condition and study that regime to learn about confinement. That is the strategy. And content is very easy. So first part, I'm studying pure YAMUs and learn about confinement of that theory in this setup. And next, I'm going to talk about QCD with fundamental quarks. And in the first part, so teaser of the first part is we can construct some reliable semiclassic without having infrared divergence if we consider that this twisted boundary condition and if size of torus is very small in the sense that n times nc times L is much smaller than a strong scale. And in that regime, so interestingly, we learned that center vortex plays an important role, which turns out to be fractional instanton. So 4D instanton splits into n fractional center vortices in this setup. And this center vortex turns out to have a close relation with monopole instanton constituent of KVB LLY Caroron on R3 times S1 setup. And we can learn about the Wilson loop, area law of Wilson loop, and n-branched structure of the theta vacuum. So let me clarify in which region I'm going to study of 4D YAMU theory. So of course, 4D YAMU theory on R4 is our main interest, but it is strongly coupled in the infrared due to asymptotic freedom, and direct analysis is quite hard. And so now we consider compactified geometry on T2, and let me call its size as L. And if L times strong scale lambda is order 1, then in this twisted boundary condition, we do not have a real infrared divergence in the perturbation theory, but still they are strongly correlated system, and confinement occurs due to very strong coupling. And interestingly, in this setup, so as long as confinement occurs, and if NC is a kind of large parameter, a lot of quantity is volume independent. So this volume independence clearly tells that computing various observables such as topological susceptibility is quite a tough problem. But on the other side, so making this size of torus small, very small, and let's say that n times L times lambda, this dimensionless quantity is very, very small, then this parameter is giving a control of semiclassical analysis, and we will see that in this regime, we can actually look at confinement explicitly using semiclassical method. And our conjecture with mid-hat is this semiclassical confinement regime is smoothly connected to confinement of strong coupling, at least for the vacuum sector, and we may be able to learn some property of the confinement from this semiclassical regime. And so let's look at this region very in detail. This is our strategy. So in order to consider our setup, so I have to briefly explain the 't-Hooft flux and what is a classical vacuum in this setup. So and it's convenient to describe the Wilson type lattice formulation to talk about the 't-Hooft flux. So this is a Wilson bracket action, but we put some center twisted phase factor in front. And this is a compactified T2 direction. So let me compact our third and fourth direction to be a finite size L. And for most of the bracket, which is vacant one, so this phase GN phase factor is just trivial. But for just this one of the bracket with shaded blue, I put a specific GN phase in front. And so basically, we are studying this lattice action in 4D, and two of the direction is compactified with this non-trivial flux along that T2 compactified direction, and study quantum field theory in this setup. And in this setup, we can look at the classical solution of this one. And it turns out that classical configuration is given by, for most of the link, it's just a trivial one. But for these let allowed link variable, you can set this link variable to be this SUN shift matrix. And for those one with blue arrows, we can take this SUN clock matrix. Then shift times clocks turns out to be clock times shift with GN phase. So this GN phase absorbs this one. So it turns out that this configuration minimizes the action. And it turns out that any classical minimum of this of this action turns out to be gauge equivalent to this setup, so our ground state is unique. In particular, center symmetry acting on this third and fourth direction Polyakov loop is preserved, and which can be explicitly seen in this setup because Polyakov loop along the third direction can be obtained by this shift matrix because it multiplies one of the red link variable. And the fourth direction is given, a Polyakov loop of fourth direction is given by clock matrix, and you can easily see the trace of P3, trace of P4 are 0. So this configuration completely preserves Gn cross Gn center symmetry. So it's consistent with the uniqueness of the classical ground state. And in order to see that this setup makes theory weakly coupled and semi-classical approximation is valid, let's look at the perturbative spectrum on this R2 times T2. And if we didn't introduce the first twisted boundary condition, KK spectrum due to this compactification for effective 2D field theory, it looks like something like this. So KK mass gap is given by 2 pi over L, and there are order n squared gapless zero modes or particle-like excitation, and we are still have to solve. So even if we integrate out non-zero KK mode, we still have non-trivial 2D effective theory, and that is in the end strongly coupled in the infrared. So with that twist, we are still have to solve quantum field theory in the infrared. But with the twist, it turns out that there are color and momentum degree of freedom are mixed up, and KK spectrum looks something like this. So KK spectrum becomes fine. So KK mass gap is given by order of 2 pi over NL instead of 2 pi over L. And more importantly, there are no zero modes at all. So if we say that our size of L is much small, and if this gap is much larger than the strong scale lambda, then you can integrate out all the particle-like excitation without going to the strongly coupled regime. So our field theory becomes almost vacant. So the effective theory becomes almost vacant within keeping the in the infrared regime. So this is a trick why first twisted boundary condition with small torus is weakly coupled field theory in the end. But still, so there is a non-trivial or non-particle-like excitation or center vortex to explain confinement, and that is an interesting part of this setup. So in order to explain it, so let me briefly talk more about this 2D effective theory. So this P3 and so Polyakov loop along third and fourth direction can be thought of the adjoint Higgs field from the viewpoint of 2D effective theory. And since they take the non-trivial wave shift and clock matrices, so SUN gauge group in the low energy SUN gauge group becomes smaller to just a center element. And importantly, this is discrete and it's consistent with the fact that perturbative spectrum is gapped. But at the same time, because of this discreteness of low energy gauge group, 2D one-form symmetry is spontaneously broken. Or in other words, Wilson loop inside R2 direction is obeying perimeter law at the classical vacuum. So in this sense, 2D one-form symmetry seems to be broken at the classical level. But with broken symmetry, so we learned that we can consider connecting different vacua of broken discrete symmetry by domain wall in the case of zero form symmetry. And in the case of one form symmetry, there is a topological solitone connecting those degenerate ground states, and they are the vortex in the case of one form symmetry. And this is exactly what we call center vortex here. And there are some interesting property of the center vortex, and it turns out that this center vortex has a 1 over n fractional topological charge. So this is not an instanton, some fractional instanton. And and still no one knows that if there is a self-dual configuration satisfying this two-foot twisted boundary condition or R2 times T2 from the analytic viewpoint, but if that self-dual configuration exists, that Yamil's action is given by 1 over n of the instanton action. And actually, so there are numerical work pioneered by Gonzalez Arroyo and his collaborators since the 90s, and there are more recent works, which suggests that so actually BPS self-dual equation satisfying this two-foot twisted boundary condition exists, and this center vortex can be really a BPS solution. And there is a more nice way to look at this self-dualness from the viewpoint of all the work by Clark, Fanbar, and Lee E about R3 cross S1 monopole instanton calculus. So let's consider SUN gauge theory on R3 times S1 with non-trivial holonomy or non-trivial Polyakov loop wrapping around this S1 direction. Then if assuming that the eigenvalue of all n eigenvalue of Polyakov loop along this S1 direction are all distinct, then in the infrared of this effective three-dimensional gauge theory, SUN gauge group should be down to maximal pattern, U1 to the n-1. Then you can classify the soliton by monopole charge of that effective U1 gauge degree of freedom. So soliton of this R3 cross S1 setup is characterized by topological charge and also magnetic charge. And what is found by these people is that so for the instanton splits into n fundamental monopoles, and those are and let me call those monopole as monopole instanton constituent of KBB LY Caron. And if we put and now compactifying this one of the direction of R3 by another S1 and imposing some twisted boundary condition so that it's consistent with two-foot twisted boundary condition, then this KBB LLY Caron monopole instanton becomes center vortex. And we can see this in this way. So let me put alpha I, so monopole charge alpha I monopole here inside this R3, and let me compactify this X3 direction. And when compactifying it, in order to introduce two-foot twisted boundary condition in this T2, we have to take center twisted boundary condition when compactifying this R3, third direction. And if this alpha I monopole emits green flux and absorbs blue flux, then this GN twisted boundary condition permutes green into blue. So it's a permutation of color. Then, so starting from alpha I monopole emitting green flux to the above direction along the third direction, then this flux piercing this twisted boundary condition turns into blue, and it again absorbs this absorbed by alpha I monopole. So this vortex-like color flux configuration is consistent with this twisted boundary condition. And actually, if you solve the classical equation of motion of this R3 abelianized Yamil theory, this configuration actually solves the classical equation of motion. And moreover, since GN twisted boundary condition gives a perturbative mass gap along 2D direction, so this center vortex have a finite size of 2 pi over NL3. So magnetic flux localizes. So if you look, and if you are living in 2D person, then this is exactly like this kind of center vortex configuration. So in this case, so center vortex, so junction of this center vortex is really a monopole, which fits into some numerical observation by Greenside, Defogran, etc., etc. So now, since we learned what is a soliton in this 2D effective theory, so we can now consider the dilute gas configuration of those center vortices. So, and importantly, since 2D effective theory is gapped, so size of this center vortex is finite. So unlike dilute gas approximation of instanton in pure 4D Yamil theory, we are not having the size moduli, and the infrared divergence doesn't occur at all. So dilute gas approximation is quite valid in this semiclassical R2 times T2 regime. And now performing this dilute gas approximation, we can obtain this expression for the partition function. So summing over n configuration of vortex and n bar configuration of anti-vortices. And importantly, so since total topological charge of this R2 times T2 setup has to be integer, but since each vortex or anti-vortex constituent has 1 over n fractional topological charge, so importantly, when summing up those gas of vortex and anti-vortex, there should be a constraint that the number of vortex subtracted by the 1 of anti-vortex has to be quantized in color number n. And otherwise, the total topological charge is non-integer, so that's inconsistent with the boundary condition. And this Kronecker delta function constraint on number of vortices minus anti-vortices can be expressed using a discrete Fourier transformation, and we obtain a non-Gn level k here. And summing up number of vortex anti-vortex gas, we obtain this spectrum of this expression for the partition function, which suggests that there are n branching structure of the ground state, and each branch has 1 over n, 1 theta over n fractional dependence of the ground state energy. So if we draw the ground state energy as a function of theta, it looks like this kind of thing, and at theta equal pi, it jumps from k equals 0 ground state to k equals 1 ground state. So Dashian's CP broken phenomena is nicely described in this 2D effective description. And this level k appearing in this discrete Fourier transform has a very important physical meaning even in 4D. So one way to understand it is if you are familiar with SPT and one-form symmetry, then introducing the background gauge field for one-form symmetry, then in the confinement phase, so this partition function should be described by some classical topological action of this background gauge field. And since it's topological, so only discrete level k modulo n is allowed, and this k is exactly the one appearing in here. And another more traditional way to understand this meaning of the k is that, so Wilson told that, so Higgs and confinement phase can be discriminated by looking at area versus perimeter law of the Wilson loop. But the confinement phase has a final classification which cannot be seen just looking at the area law of Wilson loop, and we have to introduce a disorder parameter by 't Hooft or 't Hooft loop operator in order to discriminate it. And in one of the vacuum, 't Hooft loop obeys perimeter law, but in another confinement vacuum, 't Hooft times Wilson loop obeys perimeter law, while 't Hooft loop obeys area law. And this level k tells that how many Wilson loops should be attached to the 't Hooft loop to achieve area law. So this is another physical meaning of this discrete level k. So here k just appears as a technical tool to express the integerness of the total topological charge, but this has a deep physics meaning in 4D to understand the details of the confinement, or what causes confinement, monopole or dion. Okay, so this is the content of 4D PIR semi-classical analysis. And let me move on to the analysis of QCD. And here, so in first part, since I told many details about semi-classical, so in second part, let me more focus on physics, especially about eta prime or U1A problem. But before that, so I have to specify what physics setup we are considering. So again, we want to compactify R4 to R2 times T2 with very small size T2. But since we now consider presence of fundamental quark, then fundamental quark violates the center symmetry. Then the first twisted boundary condition basically tells that we are twisting by the center symmetry. So naively, so existence of fundamental quark prohibits for us to take the twisted boundary condition. So we have to do some trick to apply center vortex semi-classics in the QCD with fundamental quark. And for this trick, so we now introduce a background gauge field of U1 baryon number symmetry and introduce a monopole magnetic flux inside this T2. And under the presence of this non-trivial twist gauge field for background gauge field for baryon number symmetry, then when identifying quark field on the right edge and left edge, not only color transition function, but also 1/n fractional power of U1 baryon transition function should appear because quark just has 1/n baryon number. And when identifying top and bottom edges, the same happens. Then we can derive cocycle condition. And if we introduce a non-trivial monopole flux inside this T2, then transition function for baryon number is constrained in this way. And substituting this expression into this cocycle condition, so color sector has Tofuft twisted boundary condition. So in this way, even in the presence of fundamental matter fields, we can introduce Tofuft twisted boundary condition for the color sector. And the center vortex semiclassics works well even in that case. Then, yeah, starting from 4D QCD, considering R2 times T2 with baryon Tofuft magnetic flux, then doing classical and perturbative analysis as we did, then for gauge sector, we obtain gapped gluon and center vortex soliton gas. And for the quark field, by solving the 2D zero mode equation under the presence of non-trivial this baryon magnetic flux, then starting from 4D, each flavor of 4D fermion gives a 2D massless Dirac fermion. Then by performing bosonization and semi-classical summation of these center vortices, we obtain 2D vector Lagrangian given by this form, where U is UNF valued scalar, which roughly contains pi, k, eta, and also eta prime. So it's not SUN, but UN, so it contains U1A, so eta prime. But it has this kinetic term, Wess-Minowitten term, 2D Wess-Minowitten term, and this is a mass term this is a quark mass term. And by summing over center vortices, we obtain this form for the eta prime potential. So this is the realization of the U1, explicit violation of the U1A. And since eta prime is massive, so if we integrate out eta prime, we get SUN level 1 Wess-Minowitten CFT as a low energy effective theory. And actually, so in 4D, assuming that this side of T2 is much larger than lambda QCD, then we can write down the chiral effective Lagrangian, assuming spontaneous breaking of chiral symmetry, and coupling baryon number background gauge field with Wess-Minowitten term, and doing this T2 compactification, then we actually obtain the same form. So same form of the effective Lagrangian as SUN level 1 SUNF level 1 Wess-Minowitten CFT. So at least, of course, we cannot prove continuity between this small T2 and large T2 regime, but at least they are consistent with continuity. Okay, then, so let me now interpret how this the meaning of this eta prime potential. So here I want to revisit the famous U1 axial problem. So U1 problem is basically saying that eta prime seems to be too massive if we regard that it's a pseudo Namb-Goldstone boson of U1 axial symmetry breaking. And the short answer to this problem is U1A is not an actual symmetry in quantized QCD because of the ABJ anomaly. So eta prime should can get a mass even if current quark mass is 0. So that part is okay, but if we look into more detail and what kind of excitation, or for example, what kind of gauge configuration really realizes the explicit violation of U1A, there would be still non-trivial, it's a non-trivial dynamical question. For example, if we think that this U1A violation is realized by small instanton contribution, then potential for the eta prime should be given by Kobayashi-Massato type determinant vertex, and it should be just cosine eta prime. But what we obtain for 2D center vortex theory is cosine eta prime over n instead of cosine eta. So compared with the conventional Kobayashi-Massato type vertex, so our result gets a 1 over n fractionalization. And if we Okay, good. If we take naive Lagian limit, so this one basically says that eta prime to the power 4 part is 1 over n squared suppressed, which is consistent with Lagian with the Venetiano result. And let me interpret how this 1 over n appears. So in the case of Kobayashi-Massagoto-Fucht vertex, we are having 4D small instanton and around it, so fermion, so this instanton acquires localized chiral fermion zero mode, and to describe those zero mode, effectively we can describe it by determinant of U. But on R2 times T2 setup with Fucht twisted boundary condition, we learned that this 4D instanton splits into n constituent. Then this localized zero mode wave function also has a bump near these n constituent of center vortices. Then, and since these center vortexes can effectively move independently, then this determinant vertex should also get a 1 over n factor attached to each location of the center vortex. So this is a physical interpretation why this 1 over n appears in the center vortex effective theory on this T2 compactifier setup. And you may wonder, what is the 4D realization? Because this center vortex fractionalization of instanton seems to be specific to this R2 times T2 to twisted setup. And there is an interesting observation that, so there is a scenario that, confining vacuum of 4D amine theory is realized by percolation or random configuration of center vortex worlds in 4D. And at least in some numerical lattice computation, this scenario seems to be plausible. Then if we are having 2D random configuration of sheets inside 4D space-time dimension, then there can be an intersection point of point-like intersection of 2D world sheet inside 4D. And in this setup, then, so if we, and since topological charge is given by E dot B, so basically, so only on this intersection point, E and B have a parallel direction. So topological charge should be localized around this intersection point. And since furthermore, center vortex magnetic flux is given by weight lattice instead of root lattice, so inner product of two weight lattice has 1 over n fractionalization, so it's consistent with 1 over n fractionalization of topological charge. So if we are having a random world sheet of center vortex and a lot of intersection points of those world sheets, then that kind of 1 over n fractionalization of topological charge happens, and this kind of scenario of fractionalization of KMT vertex also can be possible. But still, so one may wonder why eta prime can have this kind of fractional dependence inside cosine, because eta prime is introduced as a phase factor of determinant of U, which is obviously 2 pi periodic. Or this 2 pi periodicity of eta prime should be a kind of gauge redundancy of this effective theory. But this vertex violates this gauge redundancy, and how are they consistent? And we can understand this solution, so we can resolve this issue by reintroducing this label K appearing in the case of Yang-Mills. So honest computation of the dilute gas approximation gives, instead of just cosine eta prime over n, but what appears is cosine eta prime plus 2 pi k over n is appearing. And so because of this mixture of eta prime and k, so shifting eta prime by 2 pi should be equivalent to shifting k by 1. So by the presence of GN label for the confining vacuum, this kind of fractionalized KMT vertex is consistent with the gauge redundancy by eating the K, by extending the periodicity of eta prime by eating K. And since time is almost up, so let me just give one example of using this fractionalized KMT vertex. So if we look at the phase diagram of QCD as a function of up quark and down quark mass, and if we use just usual Kobayashi-Massagoto-Fucht determinant vertex, then if you look at the large mass regime at theta equal pi, spontaneous CP breaking is restored, which is inconsistent with the recent discrete anomaly matching condition. But if you fractionalize KMT vertex, then at any mass, if we go to theta equal pi direction, Cp is spontaneously broken. So difference of using determinant or fractional determinant affects the phase diagram. So this is the case of theta angle, but maybe more physical, it may even affect more physical setup. So it would be interesting to explore what is the physical, what is really physically meaning of this eta prime potential. So let me summarize. So studying on R2 times T2 with T-Hooft flux is giving a nice semiclassical, nice analytically computable regime of 4D strongly coupled gauge theories. And we look at the center vortex plays an important role, and it's deeply connected with monopole instant of KVB LLY Caroron. And I'm hopefully gave a fresh perspective of U1 and eta prime physics. And this setup can be also be applicable to other representation of fermions, and studying those results, it turns out a large N orbital equivalence turns be consistent. So studying this setup may give a new perspective of 4D gauge theory. That's everything. Thank you very much for your attention.
Time for some questions. Okay, I can start things off. Yeah. So your setup seems quite reminiscent of twisted Iguchi-Kawai setups.
Yeah.
And one thing that I remember hearing in that context is that doing a minimal twist actually is not so good as you take large N. So what happens in your setup if you have a non-minimal twist?
Yeah, so that's an interesting question. And honestly, I haven't studied yet deeply, but so one possibility is in the case of minimal twist, this gap is just given by 1 over NL, which is small, and and if N is sufficiently large, then fraction as an intermediate regime of L, then fractionalization given by Gross-Pisarski-Yaffe one-loop potential can compete the classical stabilization due to twisted boundary conditions. So that may violate this applicability of the classical analysis if N is sufficiently large. But hopefully if N is not too large, it would be okay. And even if N is large, if we consider a more judiciously choosing to first twist, maybe this.
It sounds fascinating. I see a question from an expert in the back.
Yeah, hi. So the case of the T2 cross R2 is mapped to the non-commutative torus case that has been studied a long time ago by some people.
Yeah.
And in that case, it's known that if you fix the flux in this way, you will find in perturbation theory what are called tachyonic instability. So typically you expect that the theory, there is no adiabatic continuity between the two regimes. The small coupling, the small volume and the large volume regime. In between, you would typically enter a phase where electric fluxes will become light and condense and then break.
But what happens if we take twist to be large?
You have to scale the twist with N, and in that case, there are ways to avoid the instability.
Thank you very much.
And in the case of T2 times R, for instance, we have studied it numerically, and you can find ways to avoid the instability.
I see.
But the twist has to be tuned appropriately, otherwise you end up in a phase that is not the one that you want. There is a phase that separates small volume from large volume.
Yeah, thank you very much. And another way to stabilize is adding adjoint fermion, right? Adding adjoint fermion is also another way to stabilize. Right. So here I just say that this should be crossover, but so with some kind of those deformation, if we can achieve this crossover, then we can still using the lesson run here to large R.
Okay. Other questions? Okay, I have one. Okay. Actually.
Sorry, I think I just missed this, but to get the multi-branch structure of the eta prime potential, was that, did you have to do that by hand? I know in the Pure-Yang-Mills case, you get it from the constrained instance.
Here I omit the detailed derivation, but when summing up dilute gas of center vortices, again, this kind of appearance of discrete K appears, and in the end, we obtain this expression, actually.
Okay, thanks.
Right. Okay, I have one more question. So do your remarks on the eta prime periodicity have any interplay that you're aware of with Zohar Komorgodski's proposal to think about baryons as quantum Hall droplets?
Exactly. Yeah. So that is one interesting application. So basically, when eta prime is winding just by 2 pi, so there should be some domain wall associated with the jump of this level k. And and because this level k is closely related to the different level of SPT states of 4D, so on top of those baryon, that pancake SUN level 1 Chern-Simon is introduced. So that is the realization of the idea of Zohar's pancake scenario.
So you're saying in your 2D effective theory, you can study baryons using this trick, or?
Yeah, but they are heavy, so it is realized by inserting Wilson loop ended by eta prime's minimal winding twisted one, vortex on the boundary. Yeah.
Got it. Thank you. We have time for a couple more questions. If there are no, if people are excited to get to coffee time, then we can have questions there. Let's thank Yuya for a wonderful talk.